Okay, which type of reaction is this? We got, what are the three types, first of all? Precipitation, redox, acid base. We good? All right. Do we need to turn that light up a little bit? Can someone grab that for me? Sorry, I forgot to. Unless you guys like it dark. Okay. So which type is this? Any ideas? What? Redox reaction because simple way. What did you say? What? Oh, redox reaction does transfer electrons. Okay. So a quick way to tell on this one, easy way, it's not what kind of reaction? It's not double replacement. But yeah, not covalent. Okay. Yeah. It's not a double replacement reaction. Do you know how to tell a double replacement reaction? Where you have some compound AB, and you can have numbers here, doesn't matter, okay? Plus another compound CD, and again, you could have numbers over here, doesn't matter. And this is just a general equation. And what happens is the first, or the cations, swap partners. So it's going to be AD plus B2D, sorry, I don't know what I'm smoking there. C2B3, for example. Good? So A hooks up with D, and C hooks up with B. That's a double replacement reaction. Two things are being replaced. Good? If it's a double replacement reaction, it's either precipitation or acid-base. If it's not a double replacement reaction, it's what? Redox reaction, oxidation reduction. That's it. Okay? For now, okay, that's the easy method. Today I'm going to show you the whole method, okay? But if you had to make a best guess, there you go. If it's a double replacement reaction, then it's not oxidation reduction. It's one of the other two, okay? So this one right here, we have two elements bonding together. We called it a combination reaction, right? You don't have to know that name. But it's just not double replacement, so. We good? Okay, if we have, let's say, H2SO4 and sodium hydroxide, and we get something else. What is this type of reaction? Well, let me just write down what we get. Acid base. What tells us it's an acid base?
We have hydrogen and hydroxide.
Yeah. Hydrogen is the acid or base?
Base.
Hydrogen is the acid, and hydroxide is the base. You have to have both, but when we're done, we get water. Because hydrogen hooks up with hydroxide and we get water. Are we good? So that's acid base. And if it's the other type, if it's not an acid base and it's still a double replacement reaction, most likely it's a precipitation reaction. So like silver nitrate plus sodium chloride. We're going to get AgCl plus NaNO3. Now, we got to realize that in acid-base reactions, in double replacement reactions, and in precipitation reactions, we start with aqueous solutions. What's aqueous mean again? Dissolves in water, right? Okay. And so these should be aqueous. That's how you can tell it's a double replacement reaction. So this is not an acid or a base. So it must be a precipitation reaction. Now we'll get in a little bit deeper. Sometimes it could be no reaction. We'll talk about that. But in this case, this forms a solid, and this is still aqueous. If they were both aqueous, no reaction. We'll get there. Okay? So this is precipitation reaction. This is acid-base. And this one is redox. Questions? Okay. So I can give you a million examples, but if you understand how to determine each one of them, you could do all the examples in the world. Do we have a question on that?
Can you explain redox one more time?
Yeah. And we're going to go a little bit deeper today, so maybe we should just do that. Should we do that? And then we'll have to do oxidation numbers and all that stuff, and we're going to figure how to do that, and then we'll understand it a little bit better maybe. Does that sound good? Okay. All right. So let's get in a little bit deeper to oxidation reduction. Also called redox. So remember this type, we have a transferring electrons, right? So let's break it up a little bit. We have the oxidation and the reduction. This is why we call it oxidation reduction. If we have an oxidation, we will have a reduction. If we have a reduction, we will have an oxidation. So reduction, and ladies and gents, when I learned this, I just could not wrap my mind around it. Because they kept saying, okay, reduction is when we gain electrons, and oxidation is when we lose electrons. Just memorize that. Well, that doesn't make any sense. Gain electrons is reduction? Come on, right? But that's what it is. But now let's make sense of it. Let's try to connect it to something in our brains. So reduction is a gain of electrons, and oxidation is a loss of electrons. Now let's think about what we know about ions. We learned about ionic compounds, right? What happens when something loses an electron? It becomes positive. What happens when something gains an electron? It becomes negative. So that means the charge goes down. It reduces in charge. That's how I remember it. So this reduces in charge. Can you make sense of that? And that's how you tell which one is oxidation, which one is reduction. And there'll be a test question, which one is oxidized? Which one is reduced? Okay? So before we get into an example, let me tell you some First of all, we need to figure out the oxidation number. And really what this number is basically the charge, guys. It's not when we're talking about ionic compounds, but basically, okay? And you guys know how to determine the charge just looking at the periodic table, is that right? Can we all do that? If you can't, please say something and I'll remind you, okay? All right, so let's look at oxidation numbers. So the first one is any neutral element in its element state, a neutral element all alone has an oxidation number of zero. Well, it's all by itself, it's neutral. Make sense? Okay? So its oxidation number is 0. An ion in an ionic compound has an oxidation number that is the charge of the ion. Oxidation number, so for an ion, the oxidation number is the charge of the ion. So what's the oxidation number for sodium?
1.
If it's just sodium, it's 0. If it's sodium in sodium chloride, it's positive 1. You with me? You get the difference between those two. So let's do the example here real quick. So if I have sodium, just sodium metal, just sitting all by itself, his oxidation number is 0, because it's all alone. If we have an ion in an ionic compound, so we have sodium chloride, the oxidation number of sodium plus is positive 1. You follow? Questions so far? Okay. The sum of the oxidation numbers in a compound is equal to the charge of that compound. So most compounds have a charge of what? 0, right? So all the oxidation numbers should add to 0. For an ionic compound, yeah, that's right. If we have sodium chloride, sodium is positive 1, chlorine's negative 1. We add them together and we get 0. Make sense? Okay? For a covalent compound, a little bit different. We'll get there in a minute. But what about for a polyatomic ion? They add to whatever the charge of that polyatomic ion is. So if we have nitrate, for example, then the oxidation number of the nitrogen and the oxidation number of the oxygen has to add to what? -1, because that's the charge of nitrate. Are we good? So the sum of the oxidation numbers is equal to the charge of that compound. Most of the time it's 0. The only time it's not is when we have a polyatomic ion. Okay? Any questions on those three? Those are the simplest three. And those are generally for ionic compounds. Pretty straightforward. The last one is for covalent compounds. We ready for it? Okay. So for covalent compounds, and it still works, the sum of them have to equal the charge of that compound. That's still true. We must consider in order. So if we have a compound that has hydrogen in it, we look at that one first. We determine what the electron or the oxidation number is for hydrogen very first. Why hydrogen? Because it's the king of exceptions. Okay? And what's its charge if it was going to be an ion on the periodic table? What would its charge be?
1+.
+1. And that's what it is here, guys. But we got to do these in order. That's the key word. In order. Whoops. A covalent compound must determine the oxidation number in order. Okay. So after hydrogen, let's say our compound doesn't have hydrogen in it. Then the next one we look at is fluorine. Why fluorine? It's the most electronegative. Okay? And its oxidation number is what? Any guesses? -1. That's it. So we don't call it 1- or 2-. This is not the charge. This is the oxidation number. So we just call it -1. Good? Not a big deal either way. Just they're basically the same, right? Okay? And if it doesn't have either hydrogen or fluorine in it, then we look at oxygen. The next highest electronegative element. What's its charge? -2. Yeah. And then after that, we do, good guess, we do chlorine, bromine, and iodine, and these guys are -1s. And that's it. We're done. That's all we have to worry about. Why don't we do nitrogen? Because nitrogen will be with oxygen, chlorine, fluorine, hydrogen, one of them. So we do it first, and then we'll do nitrogen later. Sound good?
So aside from the nitrogen we do later, these are the diatomic molecules.
What's that?
So aside from excluding nitrogen from this list that we'll do after we do all of these first, these are the diatomic molecules.
Yeah, they are except for nitrogen, right? Yeah, excluding nitrogen. I didn't even connect that. Good. But not nitrogen. Yeah. Okay. Before we do an example, let's talk about why we call it oxidation reduction. Let's say we have some iron, and we have a lot of oxygen in the atmosphere. We're going to get iron, let's say iron not 2. Iron 3 oxide, for example. What is the oxidation number? In fact, let me just say this without oxidation numbers for a minute. What happens when iron oxidizes? Do you know what we call that? Rust. Yeah. Iron oxidizes, becomes rust. So guess which one is oxidized? Iron oxidizes. That means oxygen is reduced. That's originally, because metals oxidize, right? That's where the name comes from. So now let's take a look at this. What is the oxidation number of iron all by itself? 0, because it's alone, right? So let's put 0 right there on top. What is it for oxygen gas? Is it alone?
No.
Yeah, the only element is oxygen. So that is considered alone. So all the diatomic molecules, they are alone. Good? So that one is also 0. Now we come over here, we have an ionic compound. This is 3 plus if we do this action, right? Remember that? We can figure out the charge, and this is 2 minus. So that means, and this is not a covalent compound, so we don't follow this, right? That means this is -3, and this is -2. Which one is reduced? I always go with the reduced first, because the reduction or reduced element is the one that is reduced in charge. Hold on, sorry. Did you guys see what mistake I made?
Did the -3 for the other.
Yeah. Saying, hold on a sec, that can't happen. Yeah, that's +3, and oxygen is -2. So we can see that oxygen goes down, right? Is lowered in charge, so that's reduction. That makes iron oxidized. We good? So does that mean oxygen's always going to be reduced? No. We don't want to memorize that. We got to figure it out. We good? Okay. Let's practice finding oxidation numbers before we get into a big one, okay? So we got CaCl2, calcium chloride. What is the oxidation number for calcium, everybody? Look at your periodic table. You don't have to memorize this.
2 plus.
Use your periodic table. So we'll say +2. Because it's in group 2, it's going to lose 2 electrons and become +2. You with me? And what's the oxidation number for chlorine? -1. Now let's see. Does this add to 0? It should, because this is an ionic compound and it's neutral, right? So let's see. We have -1 multiply 2 is -2, plus +2 multiply 1 is +2. That makes 0. Works. Just a way to check. Okay? With ionic compounds, I think it's a little bit more straightforward. Didn't say easy. Should we try a harder one? Maybe a covalent compound? So we got carbonate, CO3 2 minus. Since this is this a covalent compound or ionic compound? This was on the test, last test. Is this a covalent compound or an ionic compound? Why?
No metal.
No metals in it. Oh, but it's charged. That means it's an ion. It's not an ionic compound. An ionic compound is made of two ions, right? You with me? Actually, we called that one polyatomic. That's what the answer was, right? A little bit nicer than covalent. But okay. So I didn't trick you there, did I? Okay. All right, so this is a covalent compound. Which one do I deal with first, carbon or oxygen? Yeah, we look at our list in order. There's no hydrogen, no fluorine. We do have an oxygen, so its oxidation number is -2. You with me? Now we got to figure out what carbon's oxidation number is. Carbon's oxidation number is always going to change. Don't memorize. In fact, is oxygen's oxidation number always going to be -2? Actually not. That's why you got to do it in order, okay? If there's a hydrogen in there, it might throw it off, depending on what it is. Sometimes it's still -2, but don't ever memorize that and just, okay, throw it in there. You got to check in order. Okay, so how many, we have oxidation number of -2, and there's 3 oxygens. That's a total charge of what? -6, plus whatever it is for carbon we can call X. You guys okay with X? And what's that going to equal? The charge of our compound in this case is -2. You with me? So now let's do basic algebra. We add 6 to both sides. And our oxidation number for carbon is, since there's only one of them, it takes that whole charge, right? It is +4. Are we good? Is everybody okay with how to determine which one is oxidized and which one is reduced? If you need a little, what do you call it? A little acronym to help you remember. I don't like it because it has nothing to do with anything. But that's me. Oil rig. Oxidation is a loss of electrons. Reduction is a gain of electrons. Okay? But I like to just think of it as reduction is reduced in charge. Oxidation is the other one. But that's me. Okay? So write that down. Maybe that'll help you to remember something. Okay? Okay, ready for an example? Okay, let's start simple. If we have sodium plus chlorine gas, and we get sodium chloride, let's determine which one is oxidation or is oxidized and which one is reduced. And this is really how you tell if it's an oxidation reduction reaction. What if you have 0 oxidized and 0 reduced? Then it's not an oxidation reduction reaction. Okay? So start by, in fact, should we make a list of steps? That be useful? Step 1, determine oxidation numbers.
Are we determining it for the products or the reactants?
Doesn't matter, or you got to do both.
Okay.
Got to do both, actually. Okay. But what one do you do first? That doesn't matter. Okay? So step 2 is determine which component or which element gains electrons. And what one is that? Reduction, right? Or you can say, rather than gain electrons, lower in charge, reduces in charge. I like that myself. Which element reduces in charge? And that is reduction. Determine which element raises in charge, or rises in charge. And that's oxidation. So maybe I'll put in parentheses. If it rises in charge, it lost electrons, right? Because you do have to know that. I think there's a question on the test to ask you which one is reduction, or which one loses the electrons or gains electrons. Has to do with that, okay? That's it. So let's do this one. Let's determine the oxidation number for sodium. What is it? 0, because it's all alone. What about chlorine gas? 0. What about the sodium and sodium chloride? Positive 1, because that's the charge of the sodium ion, because this is in an ionic compound. What's the oxidation number for chlorine? Negative 1. So which one is reduced?
The chlorine.
Chlorine is reduced in charge. And that means the other one is oxidized.
Would a cation normally be the one that's oxidized?
Yeah. Yep. If they're all ionic compounds. If you have covalent, then kind of throws a wrench in the transmission there. Okay? We good? All right. Let's try a harder one. SO2, sulfur dioxide, plus oxygen gas gives us sulfur trioxide. So no ionic compounds here. Okay. Which one do you want to count first? Or which one do you want to figure out first?
The oxygen.
Oxygen has an oxidation number of 0. Good. Now let's do SO2. Out of sulfur and oxygen, which one do we know? Oxygen has an oxidation number of what? Only if it's by itself. We have to look at this right here. Oxygen is -2. Can we just know it's a -2 by looking at the periodic table? If it doesn't have any of these other elements in it, right? So that's -2. And there's 2 of them, so that's a total of -4. That means the sulfur has to be what? Why?
So that way it's neutral.
Because it's neutral. It's a neutral compound, right? Are we good? All right. So now let's do the same thing on SO3. Oxygen is -2, multiply 3 is, that means sulfur is +6. Okay. Which one is reduced?
The, oxygen is reduced.
From here to here. This one's -2. That one doesn't really reduce. But we're just saying on from this side to this side. So pick one of them. So this oxygen goes from 0 to -2. That's reduced. And we can see that this sulfur goes from +4 to +6. That's not reduced, so that's oxidized. Good? Okay, let's take a look at our worksheet. And we have 4 more examples. We want to determine the oxidation numbers of each atom, and then determine which species is oxidized and which one is reduced. So same thing we just barely did. Yep, right here. Come, if you need one, come grab one. Anybody else? Yeah, okay. Mm-hmm. Okay, which one of those you want to do together? It could be all of them. But remember, you need to get the practice.
Why don't we take into account the oxygen of SO2?
So, what do you mean?
Like, when we're comparing like the oxygens of like the first half to the oxygen.
So why don't we go from here to here?
Yeah, like include that.
You just need to do one. But if we go from -2 to -2, it doesn't transfer electrons, right? It stays the same. So if all of them stay the same, that's how you know it's not an oxidation reduction. So we only look at the ones that there's a change.
Okay.
So that's why we went from this one to this one, because we do have a change. Make sense?
Yeah.
And just one of them has to be different. If none of them are different, this is not an oxidation reduction reaction. Good? Did you want to do one of these together? Actually, there's 8 of them. Sorry, I didn't, not 4.
Can you do the first one on the top left-hand corner?
Yeah. H2 plus Cl2, this one right here,
Yeah.
gives us HCl. Okay, what is the oxidation number for hydrogen in hydrogen gas in H2? 0, right? What is it for chlorine in chlorine gas? Also 0. Then this is a covalent compound or ionic compound? Yeah, it's covalent. If you recognize it as an acid and say it's ionic, you'll still get the same answer, okay? It still works for this one, okay? So we look at hydrogen first or chlorine first? Hydrogen, it has a oxidation number of +1. That means chlorine must be -1. So which one is reduced? Chlorine goes lower, so that one's reduced. Oxygen is the other one, so it's oxidized. Not oxygen. Hydrogen is the other one, so it's oxidized. Try some of those. If you want to do more together, we can.
What about the last one on the left has bromine and iodine in it?
Okay. You want to try that one? So we have bromine gas, or liquid actually, plus potassium iodide gives us potassium bromide and iodine. Okay, where do you want to start? Bromine has an oxidation number of 0. Now which one?
Potassium iodide has +1 for potassium and a -1 for the.
Do we get that? This is an ionic compound, so we just use the charge. Same thing over here. This is +1, and this is -1. And what's iodine? 0. So what kind of reaction is this? Is this oxidation reduction? Yes or no? Do we have a transfer in electrons? If we have a reduced and an oxidized, then yes, it is. Is there any that's reduced?
Bromine is reduced.
Bromine goes from 0 to -1. If there is reduction, there is an oxidation. So that's reduced. And which one is oxidized?
The iodine.
Iodine. And we can see potassium doesn't really change, right? Does that make sense? So how do you get good at these? Just do them and do them and do them. Feel like you're good, then you do them some more. Okay? Yeah.
Can we do the top right, pentachlorid? Hydrogen chlorine?
Yeah. HCl plus Fe gives us iron 2 chloride and hydrogen gas. Okay, let's just start from left to right. So here we have a covalent compound. We start with hydrogen or chlorine. Hydrogen has an oxidation number of +1. That means chlorine's is -1. Now notice we keep every compound, everything separate, right? So we start over on iron. What's iron's oxidation number? 0. Then we start over and go to the next compound. So we have iron chloride. Does it matter which one we do first? No, this is an ionic compound, so we just use its charges. Do we know the charge of any one of those? Chlorine is what? Okay, -1. Does this look like this, guys? It kind of looks like what we do it there, right? You can do that. So yeah, we just -1 times 2 is -2. This side has to be +2. And there's only one of them, so it's +2. Do you get that? Okay. And hydrogen gas is 0. So which one is reduced?
The hydrochloride.
The hydrogen goes from 1 to 0. Notice it doesn't go negative, but it's still reduced, right? Still lowered. So which one is oxidized? The iron. Oxidized. Does that make sense?
Could you say that the chlorine was also reduced?
The chlorine goes from -1 to -1.
Oh, so it doesn't matter that if it has 2 and it becomes -2?
No. That's just how you figure out the oxidation number of the other one. Yeah, good question.
That's why I was a little confused with that one.
Yeah, no, that's a great question.
Thank you.
I want to do one more that's, I don't know that it's on here, but just in case it comes up. C3H8O plus oxygen gives us H2O and carbon dioxide. These ones are probably the ickiest ones, guys. So let's pay attention here, make sure we understand this. If we have any questions, then stop me anytime. Okay? So I'm going to start from left to right. What do we start first? Carbon, hydrogen, or oxygen? Hydrogen has an oxidation number of
Negative.
+1, because it's in group 1, right? Okay? Then we have 2 more unknowns. That means we have to go to the next one. We can't figure out 2 unknowns with only 1 known. It's like algebra, right? So we know oxygen has an oxidation number of what? -2. We have to put that in there because we don't have enough known information. Good? All right, so now let's figure out carbon. We have +1 times 8, that's +8, plus -2 times 1, that's -2, plus whatever it is for carbon, but we have to multiply that by 3. You with me? Questions on how I set that up? And what does that have to equal? 0, because this is a neutral compound. Does anybody have any questions on that? How I set that up? Okay? All right. So let's do the algebra. We have 8 and -2 make +6. We subtract 6 to both sides. Oh gosh, this one isn't a tricky one. We subtract 6 to both sides and we get 3x is equal to 6. Divide 3, we got x is equal to 2. That means the oxidation number of carbon is +2. Well, let me change this for you. I want a hard one. One that looks icky. I mean, that was the hardest one so far, right? Do you have a question on that one? Let's just say we have propane. Burn with oxygen, and we get water and carbon dioxide. Now, hydrogen is +1 again, right? +1 times 8 is +8, plus whatever it is for carbon, multiply 3. That has to equal 0. Okay? Now we subtract 8 to both sides, and we got 3x is equal to -8. Divide 3 to both sides, and we got x is equal to -8/3. Can we have fractions? The answer is yes, we can. We don't like them, but we can. Okay? But it doesn't matter, guys. It does not matter. It's -8/3. We come over here, this one's still 0, right? And then oxygen is +1. There's 2 of them, so that's +2. That means oxygen has to be -2. Are you following me? Am I going too fast? I can. Go slower. Now we go to carbon dioxide. Which one do we try first, carbon or oxygen? Oxygen has oxidation number of -2 times 2 is -4. That means carbon is
+1.
+4. Which one's reduced?
The oxygen.
Oxygen goes from 0 to -2, so that's reduced. Which one is the other one?
The carbon,
Carbon goes from a negative number, who cares what it is, to a positive number. It goes up. That's oxidized. Are we good? Yeah, Betsy.
So, the oxygen, the diatomic oxygen, how do we know it's reduced to the CO2? Because it's in the,
Because this is the only oxygen on the left side, right?
yeah.
So it can either go to this one or it can go to this one.
That would be accurate in both instances.
Yeah, yep. And it's not gonna, well, either one, yeah, we could have went to either one, but it's the same for both, right? They both go to -2. So yeah, it doesn't matter. Just noticed one that it changes. So in that case, both of them change, right? But they both are lowered, so oxygen is still reduced. Great question. How are we feeling on oxidation reduction? Do you want to try another one? All by yourself or together? Okay, yeah, do it. We actually got to get moving so we can finish today's stuff. But I'll let you finish this last one. And then if you want an answer, let me know. Okay, how we feeling? You want some answers? Which ones?
Can you do the one on the right-hand side, third one down?
Yeah. So for H2O2, it goes to H2O and O2. So the oxygen is oxidized and another oxygen is reduced. What? So oxygen is both oxidized and reduced in that one. But you can see one of them goes down, one of them goes up, right? So that's just the way it is.
Which one, sorry?
In the H2O2 goes to H2O plus O2. So their oxygen is both oxidized and reduced. Good? Yeah.
Could you do the bottom right one?
Yeah. So oxygen is oxidized, nitrogen is reduced.
So when it comes to a polyatomic ion, do we look at it as a polyatomic ion or separate?
Should we do that one?
Yeah.
Okay. So we get NaNO3 goes to NaNO2 plus oxygen. All right, let's start over here. In sodium nitrate, sodium has an oxidation number of +1, right? Then nitrate altogether has an oxidation number of what? -1. It has to.
So you look at it as the whole.
Yes, so now we can keep this, well, this is just NO3 minus, right? That's nitrate. So now we can treat that as a covalent compound, right? So oxygen is -2. There's 3 of them, so that's -6. Plus something for nitrogen has to equal -1. So we add 6 to both sides. So nitrogen is +5. Do you get that?
I was confused on that.
Should we try the next one? So sodium is still +1. Oxygen is still -2. -2 multiply 2 is -4. Plus whatever it is for nitrogen has to equal, this is nitrite, is still -1, right? So add 4 to both sides, and we got +3. So which one is reduced? Nitrogen goes from +5 to +3, so it's reduced. Good?
Yeah, thank you.
Everybody follow that, or did I go too quickly? Okay, ready to move on? What about other ones you want the answer to? Okay? Yeah, let's move on. So that's oxidation reduction. Next, let's talk about more about let's do precipitation reactions. Okay, so first of all, we need to determine what is soluble in water. Because if it's soluble in water, then we're going to say it's aqueous. Follow? If it's not soluble in water, if it's insoluble, then it's going to turn into a solid. And that's how we know which one turns into a solid, or if any does. If nothing turns into a solid, is this a precipitation reaction? No, it's not. Okay? You have to get a solid. Oh, and I didn't bring my precipitation. Gosh, dang it. I was going to show you that. Urgh. Gosh. All right, I'm sorry, guys. Such a junky teacher. Okay, I'm sorry. Okay. Know that I'm going to give you a little table. Make sure you know this. And it's not a ton. So let's keep things simple here. So soluble ions on the left side. And what does soluble mean? It dissolves in water. Okay? And the exceptions on the left side, on the right side. Okay, the first one are group 1 ions. So this is like hydrogen, lithium, sodium, potassium, etc., right? All of the group 1 ions. These ones are soluble in water. And what's the exceptions? None. Why is that? Because these are highly reactive elements, right? They're going to dissolve. They will. Okay. Next one are a few polyatomic ions, not all of them. We have ammonium, NH4+. We have nitrate, NO3-. We have acetate, which is C2H3O2-. And we have perchlorate, ClO4-. These guys are soluble in water with, again, no exceptions. Those are nice. Are we good? Okay, halogens or halides. So we got Cl-, Br-, and I-. Notice F- is not on there because fluorine is just partially soluble. So compounds with these guys in it are soluble except when it's bonded to the following: silver plus Hg2 2+, and lead 2+. So when it's bonded to these guys, it will form a precipitate. It will form a solid. Okay? But with everything else, it's soluble. Does that make sense? More practice. We just need to practice some so we can make sure and use this, yeah? Okay, and the last one is sulfates, SO4 2-. And these sulfates are soluble except when bonded to strontium 2+, barium 2+, Hg2 2+, and lead 2+. So what happens if it's not on this chart?
So,
We're going to say it's insoluble. It's not. It will not dissolve in water. Good enough? So that's all you need to know. Everything else we'll just assume is insoluble. Does that make sense what those words mean? Soluble and insoluble? Soluble means it dissolves in water. Insoluble means it doesn't dissolve in water. So it's just going to remain a solid. Okay? So let's do a few examples here to kind of, y'all have these in your notes? So let's take NH4NO3. Is this soluble or insoluble?
Soluble,
Soluble because of what?
because of the, ammonium.
And because of the nitrate, right? These guys are insoluble without exception. What about lithium hydroxide? Soluble because of what?
The lithium.
The lithium is a group 1 element. What about PbCl2?
Soluble.
It's not insoluble.
Insoluble because of what? Because chlorine is normally soluble, right? But the exception is with lead 2 plus. Is this lead 2 plus? Well, if you can't see it, then you do this, right? And we see that's lead 2 plus. Good? And what about FeOH3, iron 3 hydroxide?
Insoluble.
Why is it insoluble? It's not on our list, yep. Good enough?
You can scroll back up.
Yes. These here?
Yeah.
So this might be something you want to put on your little card, right? Write it small. Just don't miswrite it. Double check it. Okay. Good? All right, let's do some examples of precipitation reactions. So let's try AgNO3, aqueous, plus sodium chloride, also aqueous. And we got to figure out what it's going to make. Let's predict the products. Does anybody know what happens when we throw a salt in water and it dissolves? What happens? It dissociates, right, into its ions. And then, so we have all of these ions hanging out in here. And if some of them form an insoluble compound, it'll come together and form a solid, right? But if they're all soluble, they'll just remain as an electrolyte and nothing will happen. Does that make sense? So let's see what happens here. Silver is going to hook up with who? Yeah, it's going to come over here, knock sodium off, and it's going to hook up with chlorine. And we have to be able to write the correct formula. So we have to know the charge of silver. That's a transition metal. Do you remember how to figure that out?
Well, the charge of, nitrate is one minus.
-1, and there's only one of them, right?
Right.
Oh, that means silver's just +1. Okay, so silver's +1, and chlorine is what?
Minus one.
-1. So what's the chemical formula? So cross the charges, it's 1-to-1 ratio. So what is it? AgCl, right? Is that going to be soluble or insoluble?
It's gonna be, insoluble.
Insoluble, that means we put what in parentheses? An S for solid. If it's soluble, that means it dissolves in water, that means it's aqueous. Good? And sodium is going to hook up with nitrate. And sodium is 1 plus, nitrate is 1 minus, so this is a 1-to-1 ratio. NaNO3. Is it soluble or insoluble?
It's a soluble.
Soluble without exceptions, right? So that's aqueous. So is this a precipitation reaction? Because we form a solid. We start with two aqueous solutions, and we end up with a solid. Good?
So how did you know which one goes in front of which? Is that because of one has the positive charge?
Yes, the cation always goes in front. Always, always. So these guys just swap partners.
So we keep the rule that we learned already?
Yes,
Metal, no
Yep.
metal? Okay.
perfect. That's why we learned that first, so we can use it here. Okay? Anything else? All right. Now let's see what actually happens here. So if I have a container here, and I put silver nitrate and sodium chloride in it, so some water here. Silver splits apart, right, from nitrate. Because it's aqueous, it dissolves, right? Sodium chloride dissolves, so we got sodium and chloride. So what can sodium hook up with?
The nitrate.
It can either hook up with nitrate or chloride, right? That's it. And whether it does or doesn't depends on if there is a insoluble compound in here, right? So since we see that silver is insoluble with this one, those guys are going to hook up. And so we'll get AgCl. Will this hook up, guys? It'll just stay dissolved in water. It really will. It won't form sodium chloride. Or sorry, sodium nitrate. It will not. Because it's still going to be dissolved in water. Now, if we get rid of the water, then yeah, we have sodium nitrate left over. Good? All right, so let's break this up into a complete ionic equation. And then what's more important, though, is the net ionic equation. Okay? So I'm going to erase this so I don't have to write it all over again. But I just showed you that to kind of see what's going on. Okay? All right. So this one splits up into Ag plus NO3. In fact, before we do this, we should probably make sure it's balanced. Okay, before we do anything else, let's balance this. Okay, so we have 1 Ag on the left, 1 Ag on the right. 1 nitrate on the left, 1 nitrate on the right. 1 sodium on the left, 1 sodium on the right. 1 chlorine on the left, 1 chlorine. It's already balanced. But make sure you balance it, okay? If you balance it at first, it's going to be balanced in the end. Okay? So we got Ag plus NO3 minus. And this one's also going to split up to Na plus and Cl minus. Are you following me? I'm just showing you in an equation what happens if you throw it in water. They all split up, right? Does this one split up? Why not? Because it's insoluble. It produces a solid, so we're going to write that as a solid altogether. AgCl as a solid. We're going to leave that as is. We only split up aqueous. This is aqueous, so we split it up. Na plus and NO3 minus. Good? So this is the complete ionic equation. Not very useful. What's most useful and what we use is the net ionic equation. You guys know what net means? Like when you guys get paid, you get net pay, right? After taxes. What do we got to take away here? Any taxes? Probably. Right. No taxes, but we take away the spectator ions, the ones that are not involved in the chemical reaction. So let's write that down. Spectator ions are the ions not involved in a chemical reaction. So let's underline all of the spectator ions. Is silver plus a spectator ion? No, because it produces AgCl, right? It's needed to make that. Is nitrate a spectator ion?
Yes.
Yes, because it's the same on both sides. It doesn't get touched. So we can get rid of that one, get rid of that one. Sodium, same thing. Doesn't get touched, we can get rid of those. What we're left with is the net ionic equation. Which is Ag plus Cl minus, and we get AgCl as a solid. Who wants an easier way? Do we understand this way? Here's an easy way. Am I going too fast? So here's my original equation. What's my product? Right there, we know that's the product because it's solid. This is still an aqueous solution, it's still dissociated in water, right? Still dissolved. So we're gonna say, okay, that's our product. And how do we get that? From Ag and Cl. Done. If you get it, use it. If that didn't make any sense, let's practice it again because it's easy, right? We okay with that? Do another one? Okay, on our worksheet, let's do, on section 5, let's do the first one. Okay, first step, we got to predict the products. Try it. This is a double replacement reaction. What happens? Cation swap partners, right? You can tell me one compound that's created.
NH4.
NH4, what does it hook up with?
Nitrate.
NO3, right? An ammonium is a 1+ ion. Nitrate is a 1- ion. So it's a 1-to-1 ratio. NH4, NO3. Is that aqueous or solid? Aqueous, because of either one, right?
Aren't there two nitrates on the left side?
There sure are. Why are there two?
To balance out the.
Because
or the-
lead is a 2+ ion. We cross charges. But are we with lead anymore? No, we're with ammonium. That means we're going to have to do what when we're done? Balance it. Right? Do you get that? Good question. So lead is going to hook up with who? Chloride. And what's the charge of lead?
It's 2+.
If we can't figure that out, we can do it this way, right? So it's 2+. So lead, 2+, chloride is Cl-. Cross the charges and we get PbCl2. Is that aqueous or solid?
It's solid.
Why? Because lead is the exception, right? So that's a solid. Okay, our next step is we got to balance this, right? Okay, we got one NH4 on each side. That's good. We have two nitrates on this side, but only one over here, so we have to put a 2 right there, yeah? So that means I better put a 2 over here, because I just have two ammoniums. So I have to have 2 ammoniums over there. Now I have 2 chlorides, and I have 2 chlorides over here. One lead, done. Did I go through that too quickly? Sorry. Do you like this way? No? Okay. If you do, write it out. So maybe I shouldn't have started with this one because that's only one of each, right? But you see I started there and I had to replace it anyway. I had to change it anyway. So maybe we should start with this compound. We have 2 nitrates. Is it okay to count nitrates all as one unit? Yes, because it's the same on both sides, right? So we have 2 over here. That means, how many do we have over here?
You got one.
We just have 1, so we better put a 2 right there. You following? Since we put a 2 right there, that means we have 2 ammoniums on the right. How many do we have on the left?
One.
Just 1, so we better put a 2 right there. And we just put a 2 right there. That means we have how many chlorines now?
2.
2. And so we look on the other side and we also have 2. Now lead is just 1 of each. So we're good. Are we okay? Okay, now that we have it balanced, now do you want to go straight to the net ionic equation? Or do you want to write the complete ionic equation? Straight to the net? No? Okay. Do what you need, guys. Do what you need to do. If you need to write the complete ionic equation first, yeah, do it. Do it. So we're only going to split up everything that's aqueous. That's it. Into its ions. So here we have 2 ammonium ions, so we're going to write 2 NH4 pluses. And we also have 2 chloride ions. So 2 Cl minus. Good? Are you all with me? Plus, how many leads do we have?
1 on each side.
1. Well, we're just doing this compound right here. So we have 1 lead, and the charge is 2+, so we have to write 2+. Plus how many nitrates? 2. 2 NO3 with the minus charge. Then I'm running out of room here, so I'm gonna write it underneath. I'll write it in a different color. How many ammoniums do I have on the right? 2 NH4 plus. And I know I'm going to split this because it's aqueous. How many nitrates do I have? Plus 2 NO3 minus. Are we going to split this compound? No, because it's solid. So I'm going to just write plus PbCl2 as a solid. What's my next step? Or do I need to give you a second? Any questions on how we got this? Kind of? What's up?
We're just breaking down the aqueous solution.
Yep, we just broke down the aqueous, that's it. And we kept this one solid. So you break it down into its ions. There's ions there, ions there, ions there, and that's it. They have to have the right charge, and since we balanced it, we have to include how many there are. This 2 goes to both of them, right? Just like in balancing. We with me? Okay, now we got to get rid of the spectator ions. Is 2 NH4 plus a spectator ion? Yes, because they're still there, right? So we get rid of those. Is 2Cl minus a spectator ion? No, that's a part of the product here. And same with lead 2 plus. We have 2 nitrates on both sides, so they go away. Good? And we just write down what's left. Everything on the left is 2Cl minus plus Pb2 plus, and what's on the right is PbCl2 as a solid. Is it still balanced? And it still should be. And if you like to just skip the complete ionic equation step, you can. Okay? But again, if that's too much, makes sense this way, do it this way. Yeah?
I just wanna make sure, like, so when we're skipping the complete ionic equation, you just mean where you break it into that second part in the red and the blue?
Uh-huh.
So, in your mind, when you're skipping that, what are you looking at?
So let me show you what I do. I'm just going to cover this so you can't see it. Kind of. Just give me some room here. This is my solid. That is my product. So I know my product is PbCl2. And how do I get that? I get it with 1 lead, and my charge is 2 plus. I get that from here. And I have 2 chlorines, or 2 chlorides. That's it.
I just wanna make sure it was that simple.
Yeah, that's simple. Perfect. Thanks for asking. But if you just like the complete ionic equation, if that helps you, keep doing it that way. Okay? Are we good? I'm gonna do one more. If we have NaCl as an aqueous solution, and let's say ammonium hydroxide as an aqueous solution, we're going to get NaOH plus NH4Cl. Which one is solid? Is NaOH, sodium hydroxide, a solid? Look at your chart. It's not because sodium is a one group element, right? One group ion. So that one's aqueous. Is ammonium chloride solid or aqueous? It's also aqueous because of ammonium and chloride, right? So it's aqueous. So what's my net ionic equation? No reaction. This is not a precipitation reaction. We call it a no reaction. Nothing happens. They just dissolve, and that's it. Are we good? All right, you ready for the last one? Or do we have another question? All right, acid-base reactions are real similar, guys. If you understood precipitation, acid-bases are pretty much the same, except for we're not looking for a solid. Okay? So we talked about what makes it acid, what makes it base, right? So if we have H2SO4, aqueous solution, plus sodium hydroxide, also aqueous solution, we're going to get Na2SO4, also as an aqueous solution because it has sodium in it, right? Plus H2O as a liquid. This is an acid-base reaction. You following? Oops. Uh-oh. Uh-oh! What happened?
Can you go back?
Uh-uh. I'll have to start over.
We're following.
Okay. Oops. I'll write it smaller. H2SO4, aqueous, plus sodium hydroxide, aqueous, gives us sodium sulfate, aqueous, and H2O as a liquid. We can see there's the acid and there's the base, right? So this is an acid-base reaction. Now let's write the net ionic equation. First off, let's balance this. Okay? So we have two sodiums right here. So we better put a 2 right there, yeah? Now let's do sulfate and sulfate. There's one apiece, so we're good there. Now let's do oxygen. We have 2 on this side and only 1 on this side, so we better put a 2 right there. That gives us 4 hydrogens on this side. We have 2 right there and 2 right there. That's 4. Are we okay? Or did I go too quickly? So there's my balanced equation. Now let's write the net ionic equation. Does this one split apart? Yes, it does. This one splits apart. This one splits apart. Does this one split apart? No, because it's not aqueous. So I can do the same thing here, guys. What's my end product? H2O is a liquid. Don't forget I have 2 of them. How do I get H2O? What ions am I going to pull? Whoops.
Hydrogen and hydroxide.
Hydrogen and hydroxide. 2 hydrogens and 2 hydroxides. This is why we call it a neutralization reaction, because we just get water. And for all neutralization reactions, all acid-base reactions for this unit is going to look like that. It might look like this, ladies and gentlemen. You see how we can simplify that? Okay. And that's it. Didn't say that's easy, but that's it. Okay, we have 10 more minutes. You want to practice some on this worksheet? Okay. Section 5 and section 6 says predict the products of the following reactions, identify. So in the second one it says, in section 6 it says identify the acid and base, write the net ionic equation for the reaction. So, and yeah, we're going to have to predict the products. Which one do you want to do? First, second, or third? First? Okay. H2SO4 aqueous plus potassium hydroxide aqueous. Okay, we got to predict the products. What kind of reaction is this besides acid-base? Can we see that it's acid-base? Acid-base, right? But what kind of reaction are acid-base reactions? And
Double replacement.
they're double replacement reactions, right? Do you know how to predict double replacement reactions yet? We take these first guys and we swap partners. That's it. But we know H is H plus, don't we? From the periodic table. And we know hydroxide is OH minus. We should know that. It's from our polyatomic ion list. We cross charges to 1-to-1 ratio, so we get water. We ever use water as aqueous? No, because it's just water, right? It's not a solution of water, it's just water. Good? And then potassium is K plus. We find that from the periodic table. You with me? Yes? No? Okay. And sulfate, what's sulfates?
So 2 minus.
SO4, 2 minus. We got to know those. Then we cross those charges and we get what? K2SO4. Is that going to be aqueous or not?
It's gonna be, aqueous.
Yeah, because of potassium, right?
And also because of this.
And because of sulfate, yeah. So there's my equation. I know which one my acid is. Here's my acid. Here's my base. And now I got to write the net ionic equation. What is it, ladies and gents? All done. Oh, yeah, we got to balance it. Yeah, we got to balance it. Okay. Can you do this? Where should we start? Where's a good place to start?
Well, you have 3 hydrogen on the reactant side and only 2 hydrogen on your product side.
Okay, so let's not start there. Let's start with potassium. We have 2 on the right. We have 1 on the left. So what do we put in front of potassium? Do you see how that took care of that problem? Aiden, you see that?
Yes.
Yeah. Okay. So now we can do sulfate and sulfate. It's 1 to 1. Okay, that's good. Now let's do oxygen or hydrogen. Doesn't matter. We have 2 oxygens here. So how many waters do we need? 2. That gives us 2 hydrogens on the left, or sorry, 4 hydrogens on the right. We have 2 here and 2 there, that's 4. This looks just like the one above, right? So ladies and gents, if you're struggling with balancing, you just need to just do this and do this and do this. If you go to Google and type in balancing equation worksheet with answers, tons of practice. Get the answers so you know you're doing it right. Anything else? Oh, yeah. And then, of course, my net ionic equation is just right here, yeah? This is my product because it's the only one that's not aqueous. How are we feeling?
When we're writing the net, do we not include the 2 in front of the H? So we don't write it as 2H?
Well, so like we did on this one, that's what I got, right?
Yeah.
Since they all have a 2 in front, can I simplify that? And that's why. Do we have any other questions? No, that's all I have for you. Go practice this. You got this. It is.
What I did for the last exam, for the Lewis dot structures on the worksheet, I get all of them and
Yeah. Do the same thing here. Yeah.
Did I get this right? I just wanted to check the second one.
So we got. So we need a 2 right here because there's 2 over here.
Oh,
So if you see that, there's 2 hydroxides.
yeah.
Yeah, that's it.